Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Usna binti Abdul Rahman with matric number AE17014. I'm from Cluster Medical Electronic Engineering from UTH University Nusin Al Malaysia. So today I will present my presentation for final year project FYP with title Abnormality of Heart Disease Classifier in PHONOCARDIOGRAM ECG Signal using MATLAB GUI. I was supervised under PM Dr. Nabila binti Ibrahim. So this is the overall of my presentation. I will start with the introduction, continue with literature review and methodology, and result and discussion, and finally conclusion and also recommendation here. So I will start with my introduction here. This is in my abstract for overall of my project. So the background of the study. So according to Department of Statistics Malaysia, this was released last year. It's showing the statistic on cause of death in Malaysia. According to the data in 2019, ischemic heart disease contribute the leading cause in death, which contribute 15%, with a total 16,325, and 69.4% is from male, while 30.6% from female. While by ethnic group, is showing that Bimiputera contribute 40.5%, Chinese contribute 14%, while Indians contribute 20.4%. This case cause of death due to ischemic heart disease, we can see that it's higher year by year. So next is poster showing the top 3 administrative district that recorded cause of death due to ischemic heart disease. The first place goes to Selangor with 4-digit total, which is 2,909. With Petaling Jaya, Ulangan, and Klang, rank the top 3 administrative. And followed by Johor with 2,384 total, and Perak 2,156. Here we can see that 4-digit representative for each district, and it will come higher and higher. So we need to have acknowledge about this to reduce the number. So the problem statement, due to this pandemic, currently hospital is packed with COVID-19 patient. So other critical heart disease are not encouraged to come to hospital to check. For first patient that initially feel the symptom of heart disease are not encouraged to hospitals for further examination. So I'm developing a system that can diagnose in a short of time with high accuracy to diagnose the new heart disease patient on what type of heart disease he or she is experiencing. So in this project, I'm focusing with 2 types of heart disease. So we go through first for the objective of this project, which is to develop a pre-system using MATLAB, SPM, and GUI that can classify support ventilation and graphic user interface that can classify type of heart disease. We classify in SBM from PCG signal, PCG database that we use. So here to analyze, it's the PCG signal or data source undergo time domain and frequency domain. In time domain, we undergo Hilbert transform, and in frequency domain, it follow with MFCC, which is Mel Frequency Cepstrum Coefficient. So the normal PCG signal is used to compare with abnormal for discussion and analysis further. So the scope of the study, the data source that we obtained for this project is obtained from University of Michigan Heart Sound and Murmur Library. Both of these website is open source, and therefore normal PCG signal or the abnormal PCG signal we obtain from website Teaching Heart Auscultation to Help Professional website. So it's we undergo time domain frequency domain to analyze and distinguish and through SVM. So we continue with literature review, a little bit of literature review. So the other feature of a normal heart for human, we have left side and right side. So we have upper side and lower side ventricular, and so here is the in heart, so contraception to separate this part, and we have valve to control the blood to flow in one direction only. So according to the past research, this in here I focus on two types of heart disease, which is mitral valve stenosis and bicuspid aortic stenosis. So in this type of both of valve located here, for mitral valve is between left atrium, and while aortic valve is between left ventricle. So past researcher has stated that mitral stenosis happen before S1 and between S2, S3 to S4, while aortic stenosis happen in the systole, which is between S1 and S2. While mitral stenosis is between diastole between S2 to S1. So here are the website, the figure of the website for obtain from Michigan, and here is from abnormal. I gain for 5 sample for mitral valve stenosis. I label this type of heart disease as case A, while mitral valve case 1, while mitral valve bicuspid aortic valve with aortic stenosis and insufficient. In short form, I call bicuspid aortic stenosis, label it as case 2. From there, we have 4 sample for case 2. So these are the conditions for mitral valve stenosis. Here can we see the difference of mitral valve stenosis, which is narrow mitral valve. The valve does not open properly. That is why we call stenosis, and blocking blood flow from coming into your left ventricle. These are the condition for the mitral valve stenosis case 1, and this is the condition for case 2. Normally, when for bicuspid, the valve has two left leaf instead of 3. In normal, it actually tricuspid, while this case is bicuspid. It's due to the patient is born with this type of heart disease normally. So we proceed to methodology. The method that we use for this project, we use software MATLAB version R2020B. This is the normal figure graph for PCG signal, time versus amplitude. We can see S1 and S2. Between S1 and S2 is systole, and between S2 and S1 is diastole, and S1 is higher in amplitude than the S2 normal. So this is the overall flow chart. Flow chart. This is block diagram, the final how it will come. So I will show you later. So in MATLAB, we are using this coding. I generate 10 of this coding for each PCG signal. So we have total 10 PCG signal. PCG signal number 1 to 5 for case 1, or PCG signal number 6 to 9 for case 2, and while PCG signal number 10 is for normal PCG signal. So we have subplot 311 to 312, 311, 312, and 313. So 311 is time domain, and here also have envelope signal, which is the Hilbert transform. Hilbert transform is showing the energy of the signal. So here is subplot 312, which is single-sided amplitude spectrum equivalent to frequency domain, and the MFCC. So we use extracting feature. We use feature dominant frequency, which we will obtain maximum frequency, maximum value, and maximum ratio from this. So for each PCG signal, we will generate 10 more graph. So I will show here. We vary in the timing, the start and the end. So here for maximum first sample for case 1, the start and end, the range is different in 1 second. So I generate 10 Excel for 10 PCG signals from source. So for case 2, the first sample duration is 6 seconds. So I vary in 1 second, 2 second difference, 3 second also. We can see here the time difference. That's how I can generate 100 PCG signal. This is how I generate more 100 sample PCG signal. Okay, I can show here. And the X limit in 312, which is frequency domain here, I vary to focus more on the peak here, on the frequency domain. So that's why if you can see the time range is different. I start 0 to 360. 2 showing the sample number 2. So yeah, to focusing in the frequency domain. You can change the coding earlier X limit for subplot 312. So here I'm showing in one shot. Okay, that's how I analyze this data. From here I analyze it and discuss further. So I continue. I continue with my slide. So for result and discussion. For the 100 sample, I just only, okay, so for time domain and Hilbert transform, only for normal, there is 10 sample, only take one average. Same also to case A, there is 50 sample, only take one, only average representing here. And case B, for 40 sample, we take one figure to represent. So for my analysis, I can state that case A and case B look similar in their time domain graph with systolic and diastolic peak. However, it can be assumed that for normal, the peak are much smoother compared to case A and case B. The pattern is repeating, right? But for case A and case B it's different. There is murmur here, if you can see in S2, and we also have murmur here before S1 or S2. That's what we analyze. While case A has a smoother peak than case B, nevertheless, this can be further identified. They are different in the frequency domain, as the time domain graph have sharp changing representing the sizable multiple frequency present in their respective graph. So continue to frequency domain, which we label as single-sided amplitude spectrum. So for frequency range is relatively small for normal, which is between 100 to 150 compared to case A and case B. However, case A has a low frequency range compared to case B, which is case A here between 400 to 600, while case B between 1000, the peak. By taking the power spectrum using the FYP method of case B, it shows maximum frequency under the specific cutoff frequency. Nevertheless, the normal graph has the lowest frequency load value. This can be acknowledged by the frequency change of peaks in case A, which represent high power. So we continue with Mel Frequency Cepstrum Coefficient MFCC. Case B has a higher power spectral range compared to case A and the normal graph. Thus, it can be seen that case B has both higher frequency and power in decibel, the unit. Nonetheless, case A shows a higher power magnitude than the normal graph, which only display higher power only at particular time. This can be deduced that case B can be categorized as a maximum frequency disease with a higher power. On the other hand, case B has a higher frequency than case A in the power spectrum. The tick of the yellow showing the higher power in decibel. So in SBM, we input, I will show you the demo. SBM, the demo from the input. So this is we load Y label 90 data and load X train data dominant frequency. I record this earlier, and this is how we generate the SPM to classify the two type of heart disease. So the process take long in this part. So after it undergo all type of SPM, so in this time it show 83.3%, but the best I get, we need to refresh first, then the best I get 86.1%. It's vary. So this is how the demonstration shows. We show in slide. So there was SBM. So for GUI, these are the demonstration I recorded earlier. So how we input in early stage for GUI, graphic user interface, we using apps. So we click design apps. These are the design I designed for the GUI, how it will be displayed. The code that we input for specific function. We show you how it will be run. So from this, so first we browse audio, which is signal 1 to 10, which is 1 for case 1, case A. Mitral stenosis, we input so it will automate for the graph time domain. The maximum is 7 seconds, right? But we can change its start time and end time 6. So here change. Then we click for frequency, domain, and MFCC. We will plot simultaneously. It shows here. So in here it also state that maximum frequency and maximum ratio state here. Then we click the predict the case. It will show case 1. So is it true that from this source of PC signal number 1 is from case 1, which is mitral valve stenosis. So we next we try from case 2. We browse for case 2. Case 2 which is PC signal sample from 6 to 9. So we just click 6 to be input in GUI here. Then we had raw, so the maximum duration 3 seconds, 4 seconds. So we change the end time here 4 seconds. We plot the time domain graph. So we generate here and plot MFCC and frequency. So it state here maximum frequency, and when we click predict the case, it is still case 2. That this sometimes it can be error for this. And for error, if we put the start time is higher than the load time, so instead the start time value should be lower than. So that's all from me. I can for the conclusion. Sorry, a little bit long. So these are the steps that this what I gained. The highest is 86.1%. From Quan Gaussian's SVM. So for GUI, earlier as demo, and for conclusion, these are the steps that we use. So there are many more type of heart disease and treatment for this system. If what recommendation that I can make, if I have an access to a lot more database for each type of heart disease, or gain more sample, so my system can be more accurate. And also if I can and find the best feature to be extract, that also will contribute to more accurately for this system. So that's all from me. Thank you for listening.